Hello everyone, and welcome to the Society of Wetland Scientists June webinar on climate change and coastal wetlands. My name is Sunita Sarkar, and I'm going to be your moderator today. The general format for this webinar will be a short introduction to SWS, followed by the 45-minute presentation by a speaker, and then approximately 15 minutes for questions and announcements. Okay, so first I would like to welcome any non-member guests who have joined us today for our quarterly free webinar. Now, normally all our webinars are complimentary for SWS members. However, once every quarter, we open up the scheduled webinar to the public. So do book your diary for the next public webinar, which is going to be held in September. Now, to give all our guests a quick overview of what the Society of Wetland Scientists is, and here's our mission, which I'm going to read. Since its founding in 1980, the Society of Wetland Scientists has continued to grow with more than 3,000 members from around the world. We are committed to providing our members meaningful resources that promote wetland education, conservation, and restoration globally. In addition to the complimentary monthly webinars, SWS membership includes full access to the Wetlands Journal, Wetland Science and Practice, and other professional journals, as well as discounted rates for the professional certification program, which I'll mention just in a few seconds, access to the regional chapter and session activities, discounted registration at the SWS annual meeting, and the opportunity to network with wetland professionals from around the world. So please visit our website, sws.org, and learn more about our member benefits, and hopefully we'll have some of you register before the next webinar. So what we're proud actually to announce that this particular webinar is already pre-approved by the SWS Professional Certification Program and is applicable for 0.06 continuing education credits that can be applied to your professional wetland scientist certification, application, or renewal. So if you want to get a certificate for this, please contact the SWS staff. And also, SWS members can get certificates for webinar recordings that you can find on our website. So you just go to the SWS website and you can go to the events and past webinars. And if you watch those, you can then get a certificate as well. And all our webinars are recorded and archived so that you can do this. So lastly, I'd like to take a few minutes to familiarize all of us with the GoToWebinar system. So on the right of your screen, you should be able to see this panel. And this is what the control panel is. The audio pane will allow you to adjust the webinar audio by using your telephone or computer speakers. At any time during the presentation, if you have a question, you can type this in the question pane. Now, these will be answered at the end of the presentation by the presenter. And so please do use it. And if you would like a copy of today's slides for your own, for yourself, there's a PDF copy in the handouts pane. Now, in order to just test that everything's working, before that, sorry, we encourage you please to use the hashtag SWSwebinar on Twitter to tweet about today's webinar, as well as to complete the evaluation survey that will pop up at the end of the webinar. So that really would be is very useful to us as the host of this webinar series. So in order to test the question pane now, if you could please just state some of your participating country, or which state or country you're participating from, so that we can get an idea of the demographics. And I'll ask Jean if she could to please tell us who those people, where people are coming from.
Yeah, I see Florida, Bangor, San Diego, San Francisco, Pasadena, lots of Californians.
Do we have any international? Wisconsin. Okay.
I haven't seen any yet.
Okay. Well, I'm from the
Washington
UK. So
State. There you go.
Okay, well, that's great, because then it's quite wide. It's not just very specifically very close to Florida. So that's excellent. So we'd like to now start off Thanks, Jean. I'd like to start off with our webinar. So it is, there you go, sorry. It's with much pleasure that I introduce today's presenter, Dr. Todd Osborne. He is an assistant professor of estuarine biochemistry at the University of Florida, Whitney Laboratory for Marine Bioscience in St. Augustine, Florida. And he maintains an appointment in the Soil and Water Science Department on the University of Florida's main campus. As the head of the Estuarine Ecosystems Laboratory at Whitney, Todd has a diverse research program focusing on biochemical processes in soil and water in the variety of ecosystems throughout Florida. Currently, he is determining how climate change affects coastal ecosystem form and function. Todd has been engaged in Everglades restoration science for two decades, with several projects investigating biogeochemical cycling of phosphorus, sulfur, and carbon within the greater Everglades. These research initiatives include fire effects on biogeochemical cycling of phosphorus and impacts to water quality and exotic species, sulfur biogeochemistry and relationships to mercury and phosphorus mobility in Everglades soils, and spatial variability of soil nutrients at the landscape level. He hails from Georgia and migrated south for graduate school, where he met his wife, a UF veterinarian and native Floridian, and they live in St. Augustine, Florida, with their two young daughters, both of whom know the local wetlands like the back of their hands, which is just excellent. So welcome, Todd. I'll now hand over things to you.
Thank you. Thank you so much. And thank you for the invitation. I want to thank the Society for giving me the opportunity to present today. Let's see, there we go. Whoops, it's touchy. All right, so the topic that I wanted to discuss with all of you today is climate change in coastal wetlands. And you're going to see a little bit of Everglades stuff in here because I can't escape it. It's part of my my career path. But I want to bring up a discussion about planning for resiliency, and not just in the face of sea level rise, but in terms of climate change in general. And first off, I really want to thank my colleagues that have worked on the things that you're going to see today. I've had a great influence on that. Dr. Lorraine Simpson, who is a postdoc in my lab here, Tracy Schaefer, who is a graduate student in my shop, Dr. Paul Julian from DEP, Caitlin Marajka, another graduate student in my lab, and Dr. Rex Ellis from the Water Management District here in St. John's. And what I really want to do is give a quick shout out to my group here, because they all make things happen. You guys know how that works. Sorry, I got a touchy mouse. Aha, there we go. All my folks in my lab here. If you are in St. Augustine, I want to extend the invitation to come see the Whitney lab. Come by and visit us. We are open arms to all wetlanders. And we have a pretty diverse group here, and we're proud of that diversity. We even have visiting students from UGA, and we're proud of that. All right, so today, and those are jokes. It's hard as a presenter on a webinar to hear crickets, but I'm used to it because I teach online, and that's kind of like the response I get from my students when I start talking about soil physics. So I will just press on. If the jokes are good or bad, I will pretend like they're good because I can't see your responses. Maybe that's good for me. Okay, the goals of my talk today. Number one, let's discuss resilience in coastal wetland systems. And then let's talk about forecasting coastal wetland changes. And to do that, I want to use a handful of relevant examples of what we're seeing here in Florida. And so this is kind of Florida-centric, but I think the processes are global. And then I'm going to end with a comment on management challenges for coastal wetlands in the context of climate change. And this is one that's really near and dear to me. So I think it will be broadly acceptable. All right, let's see. Next slide for me. Okay. I apologize. That's going to be a little tough. So let's define resilience. I'm sure everyone has been bombarded by this term in the last couple of years. It is a hot topic. And really, as defining resilience or resiliency, it's the capacity to recover quickly from difficulties or toughness or a particular stressor, right? And the ability of a substance or object to spring back into shape. And we think of that as like elasticity. Now, that's in the broad application. But when it comes to people, we're pretty amazing. Humans are really great at being resilient. This is my joke about resiliency from the human species perspective. We can overcome and adapt, right? However, that's really not what we're worried about when it comes to climate change in our environment. We're more concerned with how things are going to respond, right? So resiliency with respect to ecosystems, capability or degree to which an ecosystem can resist perturbation and remain within the functional boundaries that characterize it. And that's really important. As wetland folks, we all have a handful of characteristics we use to define and characterize wetlands, and they're important functional characteristics. So the amount of change a system can undergo and remain in the same regime or retaining the same structure, function, and feedbacks. And we all know that those functions and feedbacks are critical to how we perceive ecosystem services and other benefits of wetlands on the landscape, right? So that's kind of what I want to do is talk about in kind of broad terms different examples of resiliency. And I'm going to show you some pictures here from the Guana River just north of my location. And I consider salt marshes to be highly resilient to perturbation in some cases. I know that's arguable in others, but this is a satellite image from Google Earth, April 2015. This is prior to any major disturbance storm-wise, and then this is December 2017. Sorry. You'll notice, and I'm sorry, these photos look better on my screen than they probably do to you, but there's no major differences in the extent of vegetation in these two photos. However, we've had two significant hurricane impacts in this area between these two photos. I make a joke that even the same fisherman is there. I guess he's plugged into the right place and is returning as well with the boat there. But in both cases, you know, we had a pretty defined shoreline edge, and if we were to get in the weeds here and actually trace these out, we'd find there's very little change in the extent of the marsh platform here after two significant storms. And when I say significant, these marshes were under 6 to 8 feet of flood surge during those storm events. And so I feel like the salt marsh is a great example of high resiliency. But there are other systems like my beloved Everglades that are kind of moderate with respect to perturbation. And we all know the examples of phosphorus impacts in the Everglades, where we shift from sawgrass-dominated marshes to cattail monocultures and the cascade of ecological effects that go along with that. But phosphorus is not the only driver in the Everglades landscape. Of course, hydrology plays a huge role in all wetlands, and it does play a huge role in the Everglades. And so on the left, what you see is the ridge and slough as we perceive it to be in its most remaining intact state. Very linear communities of sawgrass and tree islands interspersed by open water, like the little picture in between. And then on the right, you see pattern breakdown, in which, in both cases, this is caused by either too much water or too little water. And a good example of that is some work by a graduate student that I had the pleasure of working with, Danielle Watts, and she published a paper back in 2010 looking at alternative stable state models for the Everglades ridge and slough community. And as you move from dry to wet across the landscape or across water management, we get a range of bistability there, in which ridge and slough actually are expressed. In the other directions, it's too wet and we end up with all open water, or too dry, we end up with all sawgrass. But very good work by her, although I did have to tell her not to abbreviate this model in her thesis. But a good example of moderate resilience. Now, an example of no resilience, or very, very poor resiliency, and I say no resilience, is things like organic soil subsidence. So here's a picture of a marsh in the upper St. Johns River that is had its hydrology altered dramatically, and you can see the organic soils are breaking down and literally flowing away in cases. But oxidation is a process that we don't come back from very rapidly, as we know, for organic soils. And the inset there on the right is a picture of a lake bed that has undergone fire. And that's another form of rapid oxidation, right? And so in those situations, we don't have a resilient factor, a bounce back from that kind of event. When soils are lost, it's a long-term process to build them back, if in fact we can. And I'm going to show you an example, another Everglades example in 20 minutes or so, about those kinds of processes, natural ones that can cause that. So a more familiar example might be the ball and trough model that we see in our ecology classes. But think about stable state. Think about moving this ball back and forth in this trough that it exists in. You push it in one direction, i.e. an ecosystem stressor, and it's going to roll back down to that stable state. And until you reach a threshold, there's no major change to the system. It tends to self-equilibrate or stabilize. And I want to use the example that's really near and dear to me, which is right here in St. Augustine. We exist at a transition zone between the dominance of salt marsh as the main coastal ecosystem to mangrove forests, which south of here has traditionally been that dominant ecosystem. And so I want to say that that's stable state number 1 and stable state number 2, both of which can be dominant vegetation communities, but we need a stressor to move that ball over. And in this case, climate is doing that very well. In fact, climate in the form of not hotter summertime temperatures, although if you're in Florida right now, you would argue that the sun is about to scorch us, it really is a function of warmer wintertime temperatures or a lower frequency of freeze events. This work was done by Kyle Cavanaugh and others and published back in 2014 in PNAS. But the observation is that mangroves are moving northward or into higher latitudes, and not only in Florida but around the globe in response to warmer wintertime temperatures. We need a hard freeze to keep mangroves at bay, and without that hard freeze, well, this is what we end up with is a transition to an alternative stable state, and in this case it's mangrove forest. And we're going to talk about this in more detail in a few minutes, but the transition can be pretty stark or dramatic, if you will. So in Florida, we kind of considered this the freeze line. If you're a Floridian, you know all about our citrus industry and how important it is. And that's been moving southward over the last few decades because of freeze intolerance of the citrus trees, right? But now we also have this buffering capacity at the coastline, so our freeze events may reach farther south in the center of the state than they do on the coast, right? Because of the thermal mass of the ocean. However, there's been kind of a reversal of that southward moving trend for citrus, in that we're not having those catastrophic or hard freeze events in the wintertime. And so now we tend to see a transition back toward mangroves on the coast in what we would traditionally think of north of that yellow line as salt marsh that we see here, and then south of that line the dominant coastal wetland would be mangrove swamp. And as we get farther south, the species distribution of that mangrove ecosystem would change a bit. But this is all moving northward along our east and west coast. And now our current transition zone is up here somewhere, where we have both mangrove and salt marsh. So that kind of brings about some questions. And these are the kinds of questions that I want to address throughout the rest of this presentation, really, and with the examples that I'm going to show you, so we can dive down in it a little bit. The big questions that come to my mind, of course, are, well, what will the effects of climate change on coastal wetlands look like? What does that actually mean? Can we detect that pretty readily? And then how do we manage that? We want to increase resiliency, right, or maximize it. And I guess one of my other questions is, can we do that? Or is this something that we just have to adapt to ourselves? And I don't mean that in a negative way at all. I'm a consummate optimist. However, the rising tide is a bit of a challenge, right? Okay, well, let's look at these examples in that context. Now in Florida, which is really interesting in terms of our geologic history, and we are really a sand-dominated system here, right? So our state's built out of a coral reef covered with lots of marine deposit. And over the last 20,000 years, we've seen quite a bit of change in sea level and in climate. So the spring divers here love to pull up woolly mammoth bones and teeth, etc., which usually give everybody a head scratcher as to when did we have a woolly mammoth roaming around Florida? Well, about 20,000 years ago, at the last ice age, and our sea level was about 400 feet lower than it is currently, which is pretty impressive. So sea level rise is nothing new here. It's just on a time scale that we're not used to. And I think about that in the short term of what we observe as a society. That does make a difference. You know, there's a lot of climate change disbelievers out there, and a part of that is that it's not easily recognizable. We talk about minute changes in temperature or millimeter changes in the sea level, and that maybe doesn't resonate with a lot of the populace. However, one of the neat things about where I am now, and if you look at this slide, I'm talking to you from this little yellow star down here. That's the Whitney Lab in the southern part of St. Johns County, Florida. And within this zone from the lab up into St. Augustine proper is that there you can see both marsh-dominated systems, mangrove-dominated systems, and intergrading systems like the mangrove picture on the bottom left of this slide, where you see something of an invasion of mangroves as they colonize a marsh platform. So we get a good transition, a tight transition here, but the actual, I would say, ecotone, mangrove ecotone, may stretch more along the lines of Daytona to Jacksonville, because we do have salt marsh south of us in patches, and we do have little patches of mangroves all the way up to the southern part of Duval County. So it's a little more spread out in this little picture I'm showing you, but you can see all the different effects in this location. Now I've shown you a bunch of pictures from Google Earth, but if we were down on the ground looking at this, for those of you salt marsh folks, you're familiar with the classic view. Salt marsh is a dominant coastal wetland community structure from St. Augustine all the way up the East Coast and around the Gulf of Mexico, etc. It's a well understood, well studied. And one of the cool things about it is we get a great opportunity to look at vegetation zonation that defines these wetlands. And I know everybody's seen this in their wetlands ecology book, etc. But you know, our low marsh is characterized by spartina alterniflora in most cases. As we transition up the low marsh into the high marsh, we see more succulents come up, like salicornia and batis. And then up in the high area, or the marsh border, where we transition into upland communities, we'll see Juncus rhamarianus and other species in some places that are kind of characterized with that really infrequent inundation and probably more brackish water as terrestrial groundwater interacts with salinity. Very classic model. We see it everywhere on the East Coast and the Gulf. And our ecosystem functions, I think, are well defined. I don't think I have to argue with the choir on this one at all, that one of the big functions of these wetland ecosystems is providing organic matter or an energy source to the surrounding marine community, right? We call this the outwelling hypothesis, that this feeds the nearshore environment with a carbon source to sustain a detritus-based food web, right? But it's also habitat, it's refugia for fish and animals. There is a significant water quality improvement associated with these marshes, and we get shoreline protection. And and storm inundation protection, right? These are all things that we, as wetland scientists, tend to promote to the public as reasons why we want to keep these wetlands in play. One of the things that I think is important to say here, though, is that the salt marsh itself really does have greater impact than on the environmental side of things. So when we think about the finances involved in salt marsh productivity, so our commercial fisheries, as well as our recreational fisheries, which in some cases are even more important financially to coastal communities than, say, the commercial. But these are more socioeconomic implications there for changes to this community. And just a quick breeze of the literature, you find a tremendous diversity of biota that inhabit these areas. Now at the bottom, I put a little, I increased the font here a tad for the carbon production or fixation in this in these marshes. 1,400 to 2,900 grams of carbon fixed per meter square per year. That's a tremendous amount of atmospheric carbon being fixed into biomass. And a lot of that biomass is exported, but there is a residual amount of biomass that is stored in the soils as organic matter and organic carbon, and we can all appreciate that from the perspective of climate change, how important that is, right? I'm looking for nods at the camera, but nobody's nodding back. Again, just like my graduate class, right? Okay, so then we think about that. It's like, oh, that outwelling hypothesis, this is the material that is so important to that process. The carbon that's stored in the environment, in these wetlands, is literally subsurface in the soils. The rest can be exported. This is just a big rack pile of senescent Spartina, and that's going to move around the marsh and be exported even potentially off the coastline. We see it washed up on the beaches. We see it out in weed lines in the ocean, and it is literally feeding through the microbial loop all of the organisms that are detrital feeders in the area. And then this is kind of simplified version of the salt marsh food web. We think about those vegetation types down at the bottom, and we're seeing the detritus and how that feeds just about everything else, right? And that's just a very simplified model. It's always more complex than this, but you can see quickly how these things work up. Phytoplankton, of course, is a big part of that detrital food web, but these vegetation communities do produce tremendous amounts of organic matter for the system. Now let's compare that to how it works in a mangrove forest. So in the case of St. Augustine, we're transitioning from salt marsh to mangrove, and we expect that transition to continue to move north until there's some significant freeze event or freeze events to push that community south again. And that may or may not happen. But you can tell just by looking, that's a dramatic change in an ecosystem, to switch from a grass-dominated marsh platform to a mangrove forest swamp. And the predominant species here, the most cold tolerant of the mangrove species found in the United States, the black mangrove, or Avicennia germinans, is the predominant mangrove species here. We also have, in the last 10 years or so, picked up quite a few red mangrove, Rhizophora mangle, and these guys are often much easier to recognize in terms of mangroves on the shoreline. They like to be a little wetter, so they live a little bit down, or thrive a little bit farther down slope than the black mangrove. However, both species are here. We actually have white mangrove too, the third species that's known in Florida, but they are few and far between here because they are the most cold intolerant. So how does that stack up? Other than the dramatic visual, well, okay, there's definitely a forest here instead of some grass. What does that mean? Well, if you're into birds, and a lot of us are, that's a great thing in terms of refugia for wading birds, rookery, spawning, cover, etc. Not so good if you're a wading bird for foraging, because you don't get down to the water surface like you do in the salt marsh. Now, water quality improvements are well documented, shoreline protection is well documented, and of course, mangroves are an organic matter source too, right? I wouldn't say that they don't feed the ecosystem, but perhaps it's a little different. You know, we see the same kind of overview. There's definitely ecosystem values there for habitat. We see quite a bit of diversity there. And the net primary productivity is somewhere around 1,700 to 2,400 grams carbon per meter squared per year. Very, very similar to the salt marsh. However, that primary productivity is stored more in woody biomass per se than in litter. And this is just a picture of some mangrove litter. The crabs are in here, and they're doing some work. And a lot of invertebrates utilize this material. However, it is a little bit different. The timing and delivery of mangrove litter to the marsh or to the intercoastal waterways, the inshore environment, is different than it is in the salt marsh. And so there's not only quality and quantity issues, but also timing delivery issues there. And so we're not really sure exactly how far that reaches in the food web, but we can imagine that there is some effect, even though that detrital food web tends to work the same way. It's leaf material, and it's a smaller subset of that overall primary productivity that's actually being added to the environment, right? A lot of that primary productivity is being stored in woody biomass, which is not necessarily available to the crabs and the shrimp, right? And so that kind of begs the big question, well, so what? You know, is that what's going to happen if, and I apologize, I'm a really sensitive mouse when I take over somebody else's screen. If marshes are replaced by mangroves, what really happens there? Well, there's some biogeochemistry of interest to me, the nitrogen, carbon, phosphorus cycles, but there's also bigger questions about the overall functioning of the ecosystem. So will organisms that rely on the salt marsh really make it? Will they make it through to this new carbon source? That's some of the work that we're doing in this lab now and other labs that are working in the area, trying to understand that. But so from the biogeochemistry perspective, I want to tell you just some quick results that we've found already, which I think are really really interesting. Now, Dr. Simpson, in her dissertation, developed a relationship here on the East Coast, looking at mangrove dominance versus salt marsh dominance versus the ecotone, and projected out that, you know, productivity estimates per hectare. And we see that the below ground in mangrove and in the ecotone are pretty tremendous. The above ground are tremendous as well. But again, the salt marsh above ground biomass is very available to the ecosystem and to the food web that it supports versus that of mangrove. But in terms of carbon sequestration, hey, this is not a bad deal, right? And we get mangroves moving in, we get a global increase in the extent of mangroves, may just equal a negative feedback to climate change, right? Mangroves are prolific in the tropics. And if they became prolific in the temperate zone, that would be pretty amazing, although that would bode well, poorly for our temperature issues. Now, one of the side effects of moving mangrove into salt marsh is they are really good at oxygenating the rhizosphere, right? They have their nematophores sticking up, exchanging oxygen all day long. And so what we've noticed is that while they do, over time, inject quite a bit of organic carbon into the sediments via root biomass, when they initially show up, they actually facilitate the oxidation of a lot of stored carbon, you know, i.e. salt marsh carbon that's stored in the soils while that process is going on. So think about, this is like mass aeration of the marsh platform soils, and we end up losing quite a bit of organic carbon. We can actually see that in areas where the mangrove trees actually look like they're the area around them is lower. It's almost like soil subsidence is going on, exactly what's going on. So we have a feeling that this is a process that's short-lived, thankfully. However, at least initially, there's a tremendous change in soil organic carbon when mangroves move in. We're not quite sure how long it's going to take them to replace that, but we're monitoring that as one of the projects here. Of course, looking at it from the soil respiration perspective, we also see that effect. Spartina coming in relatively low compared to the mangrove areas, and we believe that part of this is to do with the size of the vegetation itself and its metabolism, but also that tremendous pumping of oxygen into very oxygen leaky root systems, right, that help promote oxidation of soil organic matter. So that's an important difference there between those two systems, and one that may just be a kind of a lag time effect. So make a couple observations about this that I want to send home with you, and that is that vegetation change induces dramatic physical, and I didn't give you a lot of data, but there are some tremendous biogeochemical changes too. Not only carbon, but nitrogen as well, which is often a limiting nutrient in the coastal environment. We're not seeing a net change in wetland area at the rate of sea level rise we have. However, we anticipate there might be a little bit of loss because our basic vegetation resistance to hydrology or to flow calculations suggest that mangroves will be a little bit more difficult and have a higher roughness coefficient, i.e. slowing water as it moves across the marsh platform. Of course, our tides are dictated, there's a time frame for that tide, and if there's resistance to that flow across the marsh platform, well, the tidal prism may in fact be lower or smaller under mangroves than it is under salt marsh. And so that's something that we're working on as well, but it could have a significant impact if we lose 10% of our wetland because of flow resistance from woody materials versus grass. Also, interestingly, a single driver, in this case is temperature, enables change of a stable state. And that has different characteristic resiliency than the historic salt marsh here. Mangroves do resist large-scale disturbance. However, freeze events can be devastating, and hurricanes as well, causing a lot of tree damage. And we did observe that here after Hurricanes Matthew in 2016 and Irma, which basically hit the entire state of Florida, I think, in 2017. For those of you in California, yes, last year at this time, I was very envious of where you are dealing with this gigantic storm. Now, management strategies, and this is where we start to get into that more gray area. My take on that is that they need to accommodate this new ecosystem and perhaps management techniques. So an exchange of information from our colleagues to the south, et cetera, is really important. And as well, there are potential significant socioeconomic components. I put my picture of my seafood here because I love shrimp and crabs, etc., and they are all dependent on that marsh platform. However, perhaps more interesting in this area, and something for management to deal with, or landscape managers, is that in this location there are, this northern portion of Florida, billions of dollars in property along the salt marsh, and the reason that property is so valuable is because of the view. And when you change a salt marsh to a mangrove forest, which, by the way, is protected from chopping down, this dramatically changes the perceived value of some of this property, and has become quite the contentious element here in St. Augustine between property owners, i.e. wealthy property owners, and their view of this mangrove ecosystem that's harshing their morning view across the marsh. So it has become something of a political thing here too. Okay, on to another example. This one relevant everywhere. Of course, I'm going to use the example from the Everglades, but it's extensive across many ecosystems. That's peat collapse. And this is where coastal freshwater wetlands are being impacted by saltwater. And what that looks like up close here is literally loss of, oops, I apologize again, loss of soil elevation after saltwater intrusion. What you can see here is sawgrass plant, and with its roots exposed, and the soil has mysteriously disappeared. Now that is troublesome for lots of reasons. One, we lose our carbon storage, and two, we are transitioning from freshwater, perhaps freshwater tidal wetlands, to more saltwater. And I want to show you what that looks like. In the Everglades, we zoom in on this transect, which is down in the middle of Shark Slough in the southern Everglades, where we transition from freshwater marsh to mangrove ecosystem. I've established just a picture show and tell transect for you. I really wish there was a better way I could do that. I'm sorry. Point number 1 is up here in the slough itself, sawgrass dominated marsh. Point 6 is out in almost open water ecosystem here, and you can see this transition zone. And it looks like this. So in the first picture, we see sawgrass and the advancement of a few mangroves here that are getting up in the area. And in frame 2, we see little ponds starting to form. Notice these little open water areas in the landscape. Still some mangroves, still some freshwater marsh. Down in pane 3, you notice that mangroves are becoming more prominent, and all of these little open water areas are opening up. I mean, it's almost like a mosaic now. In pane 4, more of the same. Mangroves expand, open water expands, and as we move through 5 and 6, you see the end result is, you know, a transition from pane 1 of 100% wetland, vegetated wetland, to roughly 40–45% vegetated wetland with quite a bit of open water. And unfortunately, this water here is too often fresh enough to keep seagrasses out, and also very tannic rich. So we're not getting a lot of productivity there, but more so losing it. Now, colleagues Tiffany Troxler and Steve Davis down at FIU put this a really awesome view or schematic of how this process likely works, because we have shallow limestone and the hydrology is altered through management, and we get these pushes of brackish water up that causes the sawgrass to die and these open water ponds to form, and that soil is lost. It's really soil subsidence. I have a bit of a different take on this. I mean, I agree with them, but I also think there's a process going on that is maybe a little more insidious with saltwater, and that is this idea of saltwater dispersion of freshwater wetland soils. Because the organic matter content is so rich, and this is just a picture of a little experiment we did in the lab with soil cores held in clear collars and subjected to different levels of salinity. And as you can tell across this picture, from no salinity to 40 parts per thousand, the expansion of that organic soil is not due to microbial processes and biogas evolution. This is literally physical expansion. And so one of the things that's important here is that we see that this process of dispersion can be very rapid. This is 7 days, and we've increased the growth by almost or the expansion of the soil by 15%. And that is a major destabilizing event, right? And Caitlin Marashka is working on that right now to bring that to publication. But that is pretty tremendous for our coastal wetlands as their exposure to salinity increases. That vegetation change induces dramatic physical and biogeochemical changes, right? Just like we saw before with mangrove advancement. However, multiple drivers enable system shift to mangroves here. There's no net gain of wetland area, and actually there's a possible loss. Now, I don't think open water is a bad thing, but in terms of productivity and carbon sequestration, those open water systems are not the same. And so, in a way, management strategies have to accommodate that. Got to view that and weigh the ecosystem services and how to do it. Now, we always fight over water in South Florida. You'd think that we had water coming out of our ears, but managing that water is a big task. And so adding more fresh water would keep that salt water at bay. However, It's not always easy to do because of nutrient issues, et cetera. There's a lot of different entities involved down there. But okay, so point being made, though, that peat collapse is significant. Now, I have another interesting example that I want to walk you through, which is sea level rise on the west coast of Florida. And this is one that, this is near Cedar Key. The yellow star here is Cedar Key, Florida. And you can see this large band along the coast, and this is actually a transition zone. And I think probably a really important thing to notice here is that within this zone, and we have a very visual cue of what's occurring as sea level rises slowly. Now this is, mind you, a very low slope environment here. And so when we move from A here across this transition to B, we're not moving up in elevation very much. We're talking about, you know, a quarter of a meter, maybe a half a meter. Very small transition in terms of elevation, where on the East Coast it's much different, right? But I want to show you what this looks like. And over this transition zone, which is probably close to a half a kilometer on the ground. It's a very wide band of change. And as we move through, let's see if I can get my graphics to work right. Well, my embedded pictures didn't show. Ah, there they go. Maybe they're just a little bit slower than I am. Okay. Imagine that. All right, so moving out of oyster bars, seagrasses, and what appear to be drowning little tree islands there in A, which is out on the edge, to B. Okay. Patience, everyone. Sorry, technical difficulties. This responds quite a bit slower on my end, I think. I'm not sure why that is problematic. Okay. Into this zone of increased salinity and isolation of upland landscapes, which are now becoming marsh and mangrove, but were once upland forest. When we get up the transect, man, wow, amazing. To see, sorry, that's painful. You can actually see the dying forest there. That's salinity-induced coastal forest retreat. That's from episodic inundation, not necessarily a hurricane, but just episodic rising tide. And in drought conditions, of course, salinity impacts and groundwater will go farther upstream. And then we end up at D, which is up at the edge, the coastal forest edge. And that's what it looks like. So we're starting to connect freshwater bodies and freshwater marshes with saltwater creeks. And along this transition, I mean, this is a big, at first was a great concern by management about this loss of coastal forest. But I don't think it's all that bleak. There's a couple of neat caveats here that are pretty positive from the perspective of ecosystem services. And the first one I want to tell you about, and the one I think is really neat, is carbon story. Okay, so when we look out across the marsh, and we know that we're moving from uplands on the left of your screen down to the marsh platform, there's this whole idea of this kind of transition, and I'm working on that. It's going really slow. But across that transition are, goodness, my apologies, our upland soils store a lot of carbon. In this picture, you'll see the Florida state soil, which is Mayaca fine sand, but the key to that state soil is that it's very prominent, formed under pine flatwood ecosystems, maritime forest, and all the way across the state. But this dark layer you see down here is called a spodoc and it's high concentration of organic carbon bound to soil particles and bound up with aluminum and iron. And so as we move across the marsh, we can see the history, the trajectory of sea level rise across these marshes, because we see things like this. This is an old pine stump that's now under salt water, and that black material you see out there is literally that spotic horizon being eroded and exposed. As you see here, this is Alexandra Rosen, a former graduate student, and Dr. Rex Ellis out in the edge of the marsh at low tide, and they're identifying that same spotic material here that we see at the surface, which was at one point buried. So there's some erosional front that comes through, and then a new depositional one. And we'll see that in the next slide. We went out and put a transect in here and actually took some really deep cores to look at that. But we go from maritime forest through a transition zone here, through the high marsh and the low marsh, and this is mean high water, right? Land surface here, along this transect, which is roughly 180 meters, right? And we saw some pretty interesting things. First off, this accumulation of material on top of the soil, which is really indicative of, goodness gracious, of the marsh. And you can see that here, what we're calling an AG, or over an EB. This is a buried E horizon, or a buried terrestrial soil horizon. And all this silty, organic rich material is on top of it. And that's out here in the marsh. If we look at these cores, though, these deep sediment cores, we can track that spotic horizon out into the marsh. We lose it here for a second, and we pick it back up again. And we're not sure what that perturbation is. Perhaps we're in an old creek bed or something. But the take home from that is that that carbon is fairly stable under sea level rise conditions. And there's a lot of literature out there that promotes the idea that soil carbon and, of course, standing stock carbon is going to be lost with sea level rise, and we accept that as solid science, and it is. But there's this little secret underground storage of carbon, which is I call it like the soil response to climate change, and that carbon is actually very, very resistant to decomposition, especially under saltwater conditions. So there's a little caveat there that's nice, that these flooding soils, as sea level rises, are keeping some significant carbon storage intact. All right, and we see that in these profiles. I'll just point out here a couple of places where that peak at the beginning of the transition zone, in the high marsh and in the low marsh, where they're located. But that percent organic carbon is fairly high for a terrestrial soil, and as it's being inundated, that carbon is staying put, and we're very happy about that. Now, those observations, again, vegetation change induces dramatic physical and biogeochemical changes, but there's a caveat there. Some carbon may be resistant to decomposition, and that's a really good thing, and that's a plus. Single driver sea level rise enables ecosystem shifts from coastal forest to coastal wetland, and there's no net wetland loss on that west coast of Florida. Actually, it's a possible gain. And so, you know, in the context of a low slope, which is unlike the east coast, the west coast is a very low slope. Our wetlands are actually expanding there. So management strategies might include encouragement of that expansion, because that's a possible gain in area to mitigate losses elsewhere. And I say that, of course, expecting lots of things to get thrown at me, and there's a caveat. It's a good idea, you know, to gain wetlands, right? But that's not the case everywhere. And I say unless you're in areas that have lower expansion potential. So let's look on the east coast. This is St. Augustine. We're built in pretty close. There are some marsh valleys and marsh floodplains and areas like out here on the edge of this picture where we might see marsh expansion with sea level rise. We're hoping so. Maybe some of this golf course will get flooded, who knows. But there are areas for marsh expansion, and that's a positive. And I say moderate because there's not a lot, not like the Gulf Coast of Florida. We're limited here. But if you go south of here, you can see what sea level rise looks like, or could look like. In the Indian River Lagoon, we're very limited with places for the coastal marshes to expand. We're built up here, right? And so some of these islands, mangrove islands, may become seagrass beds here in the not too distant future. And some areas, coastal parks and coastal lands that aren't super well developed may provide areas for expansion, but it's very limited. The apocalyptic view, of course, is if we look south to like South Beach, Miami. there's zero potential for coastal marsh expansion or coastal wetland ecosystem expansion here. And this is all seawall, and there's no shoreline at all. And so if we're not careful, you know, all of Florida could look like this if we don't manage that sea level rise and climate change with that expectation. That's kind of one of my big take homes. Okay, so high slope areas will have abrupt transitions with potential loss of these vegetation communities. And I say that we have to prioritize protecting those zones of expansion. Because if they're not there, and we don't put them in our planning process, we won't have them in the future. Low slope areas will transition, and I think that transition is pretty predictable, so we know what's going to happen as long as that room to expand is there. And so I make a call to all of our managers to prioritize protecting the low slope areas and the open areas for expansion, because they'll be important for mitigating losses elsewhere. There are places that are so built up now that we're not going to get that process happening. Okay, so our take homes. I'm going to wrap it up. Sea level rise is forcing landward migration of coastal wetlands. This is nothing new. We all know it's going on. And management of those coastal development to allow for this expansion is absolutely critical. That's my soapbox for the day. Now, climate change can reduce resiliency, and that's requiring us to adaptively manage our approach, especially depending on our goals for coastal wetland management in certain areas. You know, the way the Everglades National Park manages its hydrology and its coastal zone is different from how Miami does, is different from Indian River Lagoon, from St. Augustine, et cetera, all the way around the coastline. And so we've got to change a little bit with this. I mean, I think climate change is happening, and we're going to have to get on board with that. Now, coastal ecosystems are dynamic, and they're evolving in response to climate change, and they're pretty much following historic trajectories, and we know what those look like, right? And I think finally the biggest take home is that we see this going on, and we understand some of those drivers, and we should take the opportunity to illustrate that to the public if we need their support, which we do in many cases, and show them what this change looks like. I think that's a really critical piece of how to handle these changes. And none of that makes for increased resiliency, other than how we look at this. From the perspective of Everglades folks, right? So quick acknowledgments here. Of course, other folks in the lab that are always helping with these projects. Two of my colleagues that I hold dear as great collaborators on these kinds of investigations, Dr. Candy Feller from Smithsonian, mangrove extraordinaire, and Dr. Nikki Dix, the research coordinator for the Guanatolomato Matanzas Research Reserve here in St. Augustine. Fantastic place to do research. So I'm going to leave you with my 50-year projected view of St. Augustine, which is now going to be all mangroves, maybe, and a tad of humor because it's not all dread, right? But it is up to us in a way, and I'll leave you with those marching orders to get people engaged in recognizing what's going on and being able to visualize, actually visualize climate change. And now a lot of that's happening on the coastlines. Okay? I really thank you for your attentiveness, for your participation, and look forward to your questions. If I can get to that slide. All right.
All right. Thank you, Todd. That was great. Let me see if I can get to that slide for you because it has your email address. Great. So thank you, Todd, for your presentation. Despite all these technical issues with the slides moving, it was very informative, and I think I hope everyone enjoyed it. I did, for sure. Before we get to the questions, because we're already at the top of the hour, if in case you, the audience, if you have to leave, please, and you haven't you haven't been able to ask a question yet, please, you can email Todd. He said he will be happy to answer your questions. His email address is stated there, so please do that. Now I'm going to move the questions over to Jean to take over, but after we're done with the questions, there are a few little things that I'd like to say. So if you could hold on for a bit, that would be great. Okay, over to you, Jean, for any questions for Todd.
Okay, thank you. I don't see any questions at the moment. If you do have a question, please type it into the questions box and send it to me, and we'll post it to Todd.
Okay, well, if sorry, Todd.
Oh, I was going to say, while they're sending in their questions, I'd like to reiterate the offer. If you're in the area, please come by the Whitney Lab, stop in and see me. I'd love to show you some of this stuff, and hopefully you get a chance to see these transition zones in action. They're pretty dramatic to view it up close.
I do have a question from Kimberly. Kimberly asks, are there any researchers in Asia that also see similar trends in mangrove incursion?
Yes, I think this is a global, really a global process that's going on. You know, there are active researchers in Indonesia, Australia, China that are observing this. And interestingly, caveat, thank you, Kimberly, for bringing this up, is that in some places on the China coast, they're actually seeing the opposite. They're seeing shifts from mangroves to spartina. It's a little more isolated than the kind of overwhelming marsh to mangrove advancement, but that's a very curious situation. And it, I would say that it also parallels something that we're seeing more and more throughout North America, which is freshwater marshes being encroached on by woody vegetation all over. So there's something to learn from this process to apply to our other systems as well.
Okay, I don't see any further questions at the moment.
Very quickly, Todd, just one question. Are there solutions to the SLR issues in Miami? And number two, are the impacts being felt further north in coastal Florida?
Well, I think we've all seen in the news the issues going on in South Florida, especially Miami, that has what they call blue sky flooding, or the king tides in the fall of the year, literally flooding parts of downtown Miami. And it's very unfortunate. However, it's a process that's ongoing, and that's probably the front lines of sea level rise impacts that we see in the media. Now, unfortunately, I don't want to make a bad joke and say, well, it's time to move. However, it's becoming apparent here in Florida that there's a bit of an exodus going on from South Florida, and a lot of people are moving and trying to get ahead of that, if they're capable, I guess. The solutions, though, we don't have one yet. There's a lot of ideas about elevating areas and doing things like that. They're very energy intensive and cost intensive, but you know, in a way, much like New Orleans, Miami is very close to being inundated on a regular basis, and so yeah, solutions are needed rapidly, as this is has only been getting worse year by year. The second part of that question, can you remind me of that one?
Oh yeah, are these like the impacts being felt further north in coastal Florida?
Well, so okay, so it just so happens that in Northeast Florida, a paper came out recently identifying our sea level rise rate as being highest in the state. And while we're not feeling you know, a constant pressure from that, we are seeing coastal forest retreat all along both coastlines of our state. And in places where that's a limiting environment, or our freshwater coastal wetlands are very limited, it's dramatic in that sea level rise impacts and frequency of storm surge too are diminishing those resources. And so here in St. Augustine, I see it quite a bit, that our neighborhoods are wisely, when they were first built here, set back from the marsh in many cases, but now that marsh is getting closer, and the elevation gradients there may not be that great. So yes, we're planning for it in St. Augustine, as well as Duval County to the north in Jacksonville. It's a hot topic with our local managers.
Thank you. Jean, if there aren't any other questions that have come up, maybe we can
no
close.
Further questions.
Okay, well, great. That means, Todd, you answered everyone's questions before they even knew they had a question. So that's great. I think, well, again, thank you very much. That was really informative for me. I knew very little about this stuff, so that was really useful for me. Oh, I need to take over. Nope. There we go. So for everyone who's still on, please mark your calendars. That's the SWS members, because this would be for members only. The next webinar is on July 19th and will be around this time as well. And that's going to be a co-hosted webinar with the Society of Ecological Restoration. So please do attend. And we're also looking forward. We're also looking for future webinar presenters and topics. So in the survey that you'll be hopefully filling in at the end, you will be asked if you want to be a presenter, or if you have any topic of interest that you'd wish us to cover, so that we can actually look for the relevant stuff, relevant people. And lastly, we are kicking off our very first crowdfunding campaign through CrowdRise to provide supplemental funds for incredible wetland ambassadors. So if you could please consider donating any amount on our campaign page, and you can go to the sws.org to see for that, as well as to see further information about what this is about. And we're also currently seeking applications for US wetlands that are already deemed special, rare, and or unique by state agencies or organizations for a Wetlands of Distinction initiative. This is quite an interesting initiative, and if it works well in the US, it will go it hopefully will also be global. And you can learn more about it at their at the website www.wetlandsofdistinction.org. And finally, I'd like again to thank you, Todd. Maybe some of your wetlands can be on this Wetlands of Distinction, or already are. And so thank you for your time, for taking out of your busy schedule to present the webinar on behalf of your colleagues as well. And thank you to all the audience for attending today. And we hope you can join us for the upcoming webinar in July. And to those who are not members by then, see you at the free webinar in September. Thank you very much. Goodbye.